Uh, Good evening, everyone. Mamta, is there any doubt? You raise your hand. Maybe we'll start in a minute or two. Let's wait for 1 minute. Okay, I think we can start now. Can anyone confirm if I'm audible clearly?
Yes, sir.
Oh, sure. Thanks. So, welcome to the live session for the course Digital Circuits. We are into week 4 now. Uh, and this course is taught by Professor Shantanu Chattopadhyay, which is who is from IIT Kharagpur, and I am Anant Singhal, a PhD student from IIT Jodhpur. And again, I'll be assisting in solving some of the assignment problems which are related to your week 4 course content. That is mostly related to the logic gates and some minor topics such as hazards and some of the parity generator topic, if I'm not wrong. So, is there any doubt from the previous lecture, or we can start? Okay, yeah, sure. I think we can start then. So, yeah, let's go to the course content. So, as we are already aware that we have covered some of the introductory part of the course, we have covered the K-map simplifications and some of the identities in the last lecture. And yeah, if you have a great control over the K-map and the concept is clear about the K-map, you can minimize any given Boolean expression in any way given to you. So, this was one of the important topic, and using the k-maps also you can also minimize the gates that are actually required to solve any expression. And using k-maps there is a phenomena to also solve the static and dynamic hazards problem. So we'll be covering those problems in this particular week. Yeah, so as the name suggests, we'll be covering some of the logic gates problem. So gates are nothing but some of the expressions that are being converted into the hardware. So you might have heard about some of the gates in your theoretical lectures, such as AND gate, OR gates, which are the basic gates, which only helps in like addition, multiplication, etc. of any Boolean expressions. So those are on the hardware level. So we'll be solving some of the problems, or we'll be solving some of the minimization of the actual gate circuits and some of the minimization of Boolean algebra again to get familiarized with it. So let's start with the first problem. Maybe you guys can also solve side by side, because this might be some simpler problems that we'll be doing, because again logic gates is like relatively a simpler topic as compared to, let's say, the flip flops or the sequential circuits that we'll be covering further. So I would hope that everyone should also solve the problem side by side as I'm doing, and type your answer in the chat box. Yeah. So here is the first problem that says the Boolean expressions a bar b plus a b bar plus ab is equivalent to what? So yeah, maybe you can take 1 minute of you, and yeah, so I already got some of the answers which are A. So yeah, this is a simpler problem which can be solved directly. So as the names as a problem says, it is a bar b plus a b bar plus a b. So what I can do is I can take common a from both of these, which will make this b plus b bar, and this is nothing but 1. We have already established this like a lot of times, and a times 1 will be equals to a. So it will be a bar b plus a, and using the property that we have, a plus a bar b is nothing but a plus b. So which is nothing but option A. Yeah. So option A is the correct answer. And as you can see now, this complex expression can be converted to a plus b, which is nothing but a OR gate. So that is why the minimization is required. If we have to, let's say, build this circuit just by watching the expression, we would have started with a, then b, then we would have done the a bar b. Then similarly, we would have done the same thing to, let's say, b bar, and then a would have come from here, and then we would have added them. So this is just these two terms. If we would have done it directly, but in reality, this whole expression is just translated to a single gate, which is nothing but having an input of a b and output of, let's say, y. So hence, minimization like saves a lot of cost in terms of actually realizing the expressions. So hence we have studied so much about the minimization and simplification techniques in the previous 2 weeks. Okay, I think this is simple. Shall we move ahead?
हाँ सर.
Yeah.
सर ए बार बी प्लस ए बी बार प्लस ए बी लिखा हुआ है, तो यहाँ हम सर ए बार बी प्लस ए कर दिए, लेकिन हम बी कॉमन लेकर के ए प्लस ए बार कर देंगे तो बी आंसर हो सकता है कि नहीं?
Okay, yeah, let's do that, whatever you're saying. So you are saying, let's say I've taken a b bar and then I've taken common b, then it will be a plus a bar, right?
जी
So it
सर.
will be b plus a b bar, and
जी.
this will be again equivalent to b plus a. So these both are exactly same.
नहीं सर, मेरा कहना है कि जो यहाँ यहाँ सर ए बार बी प्लस ए इंटू बी प्लस बी बार किए ना, तो ए बार बी प्लस ए हो गया,
Yeah. Yes.
और सर हम अब बी को, अच्छा, ए प्लस बी बार, हाँ ठीक है सर, ठीक 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 सर, समझ गए समझ
Okay.
गए.
No problem.
ओके ओके.
You can please mute yourself.
हाँ हाँ.
Yeah. So we have the next problem. I think some of you have already. So one of the participant is saying D. So yeah, again, this is one of the simpler problems. So it says x plus y, x plus z. This is even a property that we even learn in the Boolean expression. So let's solve this out. So the first will be x plus xz plus xy plus yz. So if I take x common from the first three terms, it will be 1 plus z plus y plus yz. And this will be nothing but 1. And this will give me x plus yz. So the correct answer would be option D. Again, this is a simpler problem that we would have done by using two gates, for example, like x and yz would have been something like this. And then, yeah, this would have been a OR gate. Instead of using two AND gates, two OR gates, and then using a AND gate. So again, this also reflects why minimization is useful. Again, was a simpler problem, so I think we can move ahead. So now this is the next problem. It says a combinational circuit implementation of the following Boolean function is which circuit? Okay, so I've already got one answer. I'll wait for some more, and then maybe I'll give you 2-3 minutes. Please try out the problem, and then we can move ahead. Okay, so most of you are saying A. So again, this is 1247. We can also do that using quickly using K map also. So let's say it is ABC. So it will be B bar C bar, then B bar C, B C, and B C bar. So 0, 1, 2, 3, 4, 5, 6, 7. So it's 1247, which is I think the cross version. Sorry. So 1247. So if I even write this in the simplified terms, it will be not the simplified, but the actual standard SOP form. It will be A B bar C, then A B C bar, then A B C, and then A B, sorry, A bar B C bar. This is nothing but it reflects to A XOR B XOR C, which is which is option A. So yeah, option A is the correct answer. Well, let's move ahead. So this is a problem related to the, it is assignment question. Are you asking or telling? I'm not sure. Are you telling that this is given in the assignment? Okay, okay, yeah, no problem. So yeah, so again, the next problem is related to the parity generator. Uh, so again, I'll give you maybe 2 minutes. If you already know the answer, you can let me know in the chat box. Otherwise, I'll solve it. Okay, so I'm getting a lot of B's. Let's see. So it says when the set of input data to a even parity generator is this, the output will be what? So parity generator is nothing. Parity means counting only. So even parity generator, sorry. So basically the even parity generator, let's say this is already written, it generates even number of ones. For example, here the problem is 0, 1, 1, 1, right? So the parity bit will be something so that the final number would be even. So final number of ones in the actual answer would be even. So what do you think we'll require as a parity bit so that number of ones will become even? Is it 0 or is it 1? No, look. So let's say the parity bit is 1 now. So then only the number of ones become even, right? For example, if the question would have been something like 0 1 1 0, and if I would have asked you the parity bit given so that it is an even parity generator, so you would have said 0 because now the whole thing has even number of ones already. But here, since the question is having odd numbers of 1, so we'll need to add that parity bit of 1 to get the numbers as even. So the answer to this problem will be, so the parity bit that will be given out is 1. So option A is the correct answer.
सर एक बार फिर समझाइए सर, नहीं समझे.
Oh, no problem. So it is asking that when the input data is fed to the even parity generator. Even means multiples of 2, right? Even number. So it is asking when we are feeding, let's say 0 triple 1 to the parity generator, what will be the output? Output is what? So even parity generator, what it do is it generates even numbers of 1. Now in the question, the input is having odd number of one, right? The number of one in this particular expression is 3. So to make it even, what this parity generator will do, it will make the parity bit 1. That is the output of this parity generator. So that now the numbers of 1 will be 4. That is actually even. Hence the output of this parity generator will be 1. As I said, if the question would already been having even number of ones, then the parity bit would have been 0 because it already has even, so it does not need any additional one to make it even. Hence,
इवन पैरिटी में सिर्फ 1 ही आता है सर, 0 भी आ सकता है?
no, we count numbers of one. So okay, so just to simplify it, let's say if you want even parity generator, that means you should have even number of ones and odd
ओके,
number of zeros.
ओके, ओके सर, ओके, ओके।
Yeah.
तो ये सर ये कितना का ग्रुप रहता है सर, 4 का?
No, it can be any bits. It depends
ओके
upon the
सर,
question.
इवन में होना चाहिए।
Yes.
ओके सर, थैंक यू।
Okay, I think we can move ahead now. This was again a simpler problem. Yes, is there any out? Yeah, we have to make it even. The numbers of one should be even. Okay, so this is the next problem. It says the input to a logic gate A is 1100 and B is 1010. What will be the output if the logic gate is NAND gate? So NAND gate, I think you are already be aware now. So NAND gate is nothing but, let's say this is AB. So the expression for NAND gate is A dot B whole bar. We got a lot of answers which are mixed. Some are saying B, some are saying C. So as you already know that AND gate, not AND but NAND gate is A dot B whole bar. That means, let's say this is two input. So if there is any bit which is 0, then the AND gate will always give 1, and if both the bits are 1, then
Option B, sir, answer.
yes, yes, let me do it. Please type your answer in the chat box. Yeah. So now A is given by 1100 and B is given as 1010. So we are having a NAND operation on it. So for example, the first one is 1 1. So when both the bits are 1, the output is 0. So this will be 0. And when any of the bit is 0 again, so the output will always be 1. So final output will be 0 triple 1, which is option B. So option B is the correct answer. Yeah. Hope it is clear. I think we can move ahead. So the next problem is the number of inputs and outputs in a half adder are. Okay, again, I've got some more answers which are mostly same. So half adder is nothing, you might be knowing that it has all the adders are gives out some sum and carry. So half adder is nothing but, let's say this is the input of a half adder. So half adder gives a sum which is nothing but A XOR B, and it gives, sorry, and it gives out a carry which is A dot B. If I, let's say if I make a box which is something called as half adder, so it will have two inputs which are A and B, and it will have two outputs which is sum and carry. Similarly, a full adder, if I again make a box for example, so it has A, B, and the input carry as a input, and then sum carry as outputs. So question here asks about the half adder circuit. So as you can see in the half adder, what do we have? We have two inputs which are A and B, and we have two outputs which are sum and carry. So the answer to this problem will be option D. Okay, so there is some query, I think. Half adder is also known as XOR gate. No, no, no. Half adder is not known as XOR gate. XOR gate is nothing. I mean, this particular gate is called as XOR gate. Half adder circuit is not a XOR gate. It is a complete circuit. So the sum of the half adder, you can say, is a output of a XOR gate. Again, this was simple. Let's move to a better problem. I think, yeah, this is a better problem. So it says the output Y in the circuit below is always 1 when what? So maybe I'll give a few minutes to all of you. You can try it out because this is a better problem, I think, and then I'll solve it.
Sir, can you explain this question?
Yes, yes, I'll do it in a minute. Yes, I'm getting mixed answers. Let's see. Some people are saying A, some people are saying B. So let's see. So again, this is a easier problem only. If you go side one by one to in the circuit. So what do we want is we want this output to always be 1. This is what is said in the question. So we'll find out what is Y and then we will equate it to 1. So whatever is Y, if we equate it to 1, we'll be able to find what is the expression that will hold for all the time. So the dot here means that it is connected. So the first input is P and Q. So the NAND output will be P dot Q whole bar. Then the second output will be Q dot R whole bar. And the third output will be P dot R whole bar. I'll just write P dot bar, P dot R whole bar here because this is the input that is being fed to the final gate. Now this is again a NAND. So if I do it, it will be P dot Q whole bar dot Q dot R whole bar and then whole bar. This is again a simpler thing. I hope it is clear. And then it is a shorted NAND. So let's say if we have a with a shorted NAND, what is the output? Can anyone tell quickly? Yeah. So it is like equivalent to a NOT gate. Similarly, it is equivalent also equivalent to a NOR gate if it is connected or shorted together. Sorry, it is a NOR gate. Yeah. So if the output of this particular thing, let's say this is maybe x, so the output of this will be x bar. So what I'll do is I'll write pq bar dot qr whole bar was the thing, and then whole bar. So what I can do is I can cancel out these two, and it will be nothing but pq whole bar dot qr whole bar. Is it clear? The output here is this, and the output here is this. Is there any doubt till now? Okay, I hope not. So now what I can say is, what is y is? Y is nothing but, oh, it's capital Y. Capital Y is nothing but PQ whole bar dot QR whole bar dot PR whole bar whole bar. Is it clear to everyone how I have written this Y? Is there any doubt? Okay, great. So I can use the De Morgan's here. I can write PQ whole bar then bar plus QR whole bar then bar plus PR whole bar then bar. So can I write y as PQ plus QR plus PR? Is it clear to everyone?
Okay, sir.
Yeah. So this expression is also what we call as three input majority gate. So now the question says, or the option says, it will be one when two or more inputs of P and Q are zero. So let's say two or more means, let's say we make P and Q is equals to zero. So then the output Y will always be zero, right? Because this is the majority gate. So if two or more inputs are one, then only this condition will hold. Let's say P and Q or Q or R or P or R is equals to 1, then Y will always be equals to 1, right? Just to explain you in a easier way, so let's say P, Q, R. So the output of the majority gate is when we have more numbers of 1. So it says basically 3, 5, 6, 7, and all the other things are 0. So it is min terms 3, 5, 6, 7. So now, as you can see, the output is only 1 when we have two or more ones in these four cases only. Hence, now the question is two or more P, Q, R are ones. So option B is the right answer. With this experiment, is there any doubt? With this explanation, we get y is equals to 0. Can you please clarify? Is it clear or? Yeah, we only get y is equals to 0 when we have more than two zeros, as I said. So for example, the red cases, if I'd like to highlight, you see in all of these four cases, there are more numbers of zeros than one in the input. So then only we'll get all output as 0. Yeah. But the question asks that y will always be equals to 1 when what? So it will be always equals to 1 when we have this yellow highlighted things. That is when we have two or more ones in the output, or sorry, in the input. Okay, explain again. Okay. So I hope it is clear that we have reached here. Like there is no doubt that the y is pq plus qr plus pr. Yeah. So let's say we have this pq plus qr plus pr. Now what I'm trying to say is when you are making a truth table of it, we are, what we want is we always want to be equals to 1, right? And let's say we feed these values one by one. So let's say if we feed p, q, r 0, all of them are 0, that means the output is 0, right? When let's say p and q are 0, so this term will be 0. Maybe I can use some other link. Yeah. So let's say I'm taking now this second case. When p and q are 0, this term will be 0, this term will be 0, and this term will be 0, right? So the output is 0. Then if I take 0, 1, 0, which is the third case, so if p is 0, then this term goes away. If r is 0, then this term goes away, and is again p 0, then this term goes away. So again this will be 0. Similarly, I made a truth table, or you can also make a K map, for example. Do you want me to make a K map? Okay. So who said explain again? Lavanya, do you want me to make a K map and explain if you're not able to understand this? Okay. Okay. So you are able to understand this now? Okay. Yeah. Fine then. So the answer would be
Sir,
option B.
explain K-map, sir.
Sorry. Uh, your voice is not clear. Can you please repeat again? Someone said something. Hello.
Explain with K-map, sir.
Oh, you're saying explain with K map. Okay. Okay. Yeah. Fine.
Sir, explain with K-map.
Yes. Yes. I got it. So let's say we are taking PQR, so it will be QR bar, QR QR, and then QR bar. So it's 0, 1, 2, 3, 4, 5, 6, 7. So now the question is PQ, which is these two one. Second term is QR, which is this particular column, and the third term is PR, which is this, right? So this is the K-map of it, and if I make, let's say, different combinations, so I can only make this, this, and this, and this is what I wrote as min terms 3, 5, 6, 7 also. This expression is already simplified. I was just trying to say that we have got this 3, 5, 6, 7 from the K-map also. So that this means that when the input is 3, 5, 6, 7, which is this 3, 5, 6, 7, the output will be 1. Hence, we want the number of ones in the input to be more than or equals to 2. Is it clear now?
Sir, can you once show the diagram, sir?
Yeah, sure.
The question is, so how we have to compulsory make it sure that we have to simplify by writing the expressions itself.
Yeah, the question says that the output of whatever the expression that we are getting should always be equals to 1. So we have to like force the input such that the output should always be 1.
So by using K-map, we can do it.
Yeah, I mean K-map is also not required. I was just trying to simplify it since we have already a simplified expression as the output. So by K-map, you can see that this is 3, 5, 6, 7. I mean, the terms that we are getting are 3, 5, 6, 7. And in all these 3, 5, 6, 7, the input, whenever the number of ones in the input is 2 or more than 2, then only we are getting output as 1.
Okay, sir. Okay.
Yeah. Someone saying why not option D? Option D says any odd numbers of input. No, any odd numbers of input, any odd number of input we can. No, it is not right, right? Because in this particular case, let's say this one also, the number of input or number of ones in the input is 1, but the output is 0. So odd numbers cannot be the answer. Similarly goes for the even. So the only answer that could be true is option B. Can you take canonical form? So canonical form here is not required because we have already simplified the expression. Or if, I mean, even if you want to, you can write this. Let's say the first term is P bar Q R plus the second term is P Q bar R, then 6 is P Q R bar, and it's P Q R. So again, it's 3, 5, 6, 7. We don't want to elaborate it because, yeah, it's already there. I mean, the simplified form is already there, and you can make a truth table out of it, something like that. I mean, you should always remember that this PQ plus QR plus QR is a 3 input majority gate, and the output will only be 1 when we have more numbers of 1 in the input as compared to 0. Is it clear to everyone now? Shall we move ahead? Okay, let's move ahead now.
Sir, can you explain please, sir, pairing of K-map?
What?
Pairing of K-map, sir. That is a
What of K-map? I don't have
pair,
knowledge.
pairing, sir. Pair.
Oh, pairing you are saying. Okay. So yeah, I mean, so yeah, this is the only, like these, let's say if we make this pair and this pair, we are only left with this. I mean, there is no other combination that we could have made. Like we cannot make a quad, that means a pair of 4 is not possible here, so we have to make a group of 2 only. That is the pair. So only these 3 combinations are possible. As I said, this form is already simplified. Don't get confused by the K-map here. If you already have this, you don't need to make use a K-map to simplify it. If this would have been the output, then we would have been needing it, but yeah, we do not need the simplification using K-map. K-map was just to show that it is 3, 5, 6, 7, and the inputs, the number of ones in the input is more than 1. Oh, sorry, more than 2 or more than 2. Is it clear? I think we can move ahead now. We have spent a lot of time on this problem. Yeah,
Thank you, sir.
yeah. So now the next problem says the dynamic hazard problem occurs in which type of circuits? So what some answers? One answer is C. I'll wait for some more and then I'll try to explain what are basically hazards. But saying B also, which is sequential circuit alone. Both A and C. A and C cannot be the answer. I mean, there should be only one answer. I think you're trying to say both A and B. Yeah. Okay. Let's wait for some more people to answer. Then I'll also try to explain what are hazards and what are the different types of hazard and how do they come.
इसका आंसर सी होगा सर.
Yes, yes. Please wait for others also to answer. Then I'll also explain. Don't worry.
सर ये डायनामिक हैजार्ड क्या होता है?
I'll explain. I'll explain. Okay, so let's maybe see what are the different types of hazards that we have, and let me give you some idea that will help you in your theoretical lectures also. So there are basically three types of hazards that we have. The major distinction is static and dynamic. In static, what do we have? We have static 0, and the second that we have is static 1. And dynamic means when both of the effects are coming. So by static 0, what do we mean is that the output should have been 0 for the whole time. Let's say this is 0 and this is 1, I mean the level. But due to some error, what happened is we are getting, let's say, maybe a small pinch of 1 as the output. So this is a static 0 hazard, because it should always have been 0, right? But the output have become somehow 1 for a short case. Similarly, static 1 is the output should always have been 1. But due to some glitch, what do we have is we have a small pinch of 0. And in dynamic, we can have both, like we can have either 0 or 1 hazards. So let me try to explain it using maybe a simple circuit. So static 0 hazard first of all comes due to expressions like variable and the multiplication of variable bar. Static 1 comes out of this, and so I mean, just to explain in a very simple way, if you see something like this in your problem, then you can say, yeah, this type of hazard will come. So first of all, for hazards to be there, the expression should always contain, let's say x is a variable and its complement, that is x bar. So in any problem, if you see like it is given a and there is also a bar in that expression, that means there should be some hazard in the problem. Is it clear, this particular line? If it is not, please let me know. Okay, I'm assuming then it is clear if you're not saying anything. So let me try to explain you using a very simple circuit. So as I said that a dot a bar, which is nothing but 0, can create static 0, right? So let's see how does it do that. Maybe I can make, let's say this is a and this is a bar, right? And this is the end. So what can happen is there could be delays in the output, right? Let's say you applied the input a, which is something like maybe this, and the a bar you are getting after some delay, which is a bar is nothing but the or the not. So there is some delay and you are getting the output as this. Are the a and a bar clear to everyone? Yeah. So if it is clear, so what you can see here is in this particular window, both a and a bar has become 1, right? So due to which the final output, which should always have been 0, the ideal output would have been 0, but due to this glitch or this delay, the output would have rose to 1 at this delayed certain instance. So this is why this is a static 0 hazard. Is it clear? Similarly, if you try to see for the static 1 hazard, so what I can make is static 1, it's a plus a complement, right? Sorry, yeah. So I can make again a and then a not. So since this is plus, so this would be a OR gate. So let's say now my a would have been something like this. So a bar due to some delay has become something like this. So now if I try to plot a plus a bar now at this particular instance, both A and A bar are 0. So the OR of this will be 0, right? So it should have been something like this. But due to this delayed glitch, the output has some delayed 0. Hence, this is a static 1 hazard. Is it clear to everyone, these two cases? Okay. So now the question that we were doing is, it says a dynamic hazard problem. So dynamic hazard is basically a combination of these two. So if these two are happening together, something like this, as I said, let's say A plus A complement. So this is static 0 and A plus A complement is nothing but static 1. So if there is both happening together, then it can be a dynamic hazard. So we'll see some problems also related to this later. But yeah, the dynamic hazard can also happen in combinational, can also happen in sequential. The condition is the variable or the expression should contain, let's say, variable and its complement, which is variable bar. So answer would be option C.
Sir,
Yes, sorry.
sir,
Yes, I can hear you.
जी सर, कह रहे हैं सर ये डायनेमिक हैजार्ड जिस तरह सीक्वेंशियल सर्किट और कॉम्बिनेशनल सर्किट में होता है, तो स्टैटिक किस में होता है सर, स्टैटिक हैजार्ड?
Static, yeah, static can also occur in, please mute yourself, yeah. So static can also occur in both combinational and sequential. The point is, it is dependent upon if you have a variable and its bar. So it can happen in anywhere. It's not dependent upon whether the circuit is sequential or combinational, it depends upon the expression. So the answer again would be C also if the question would have said static.
ओके सर,
Yeah. Oh, hazard in general English term, it's like danger, right? So hazard means something which is not desirable. So you always wanted a 0, but you are getting a 1 for a short time. You always wanted a 1, but you are getting a 0 for a short time.
Wow.
Um, is it clear? Who sir asked? Manikanta, is it clear? Please kindly respond so that we can move ahead. Okay, yeah, thanks. So let's move to the next problem now. Okay, so it says in the figures shown, the output Y is required to be something like this. The gates G1 and G2 must be respectively what? So again, maybe I'll give you 5 minutes. Try to solve this problem and type your answer in the chat box. I have already got one answer, but yeah, let's wait for some more answers and then I'll also proceed to solve. Okay, so I got some answers as A. So let's see. So it says in the figure shown, the output Y is AB plus C bar D bar. So the gates G1, which is this, and G2, which is this, must be respectively what? So let's see. So the input of G1 is whatever we can tell. So it is A bar, this is B bar because this is a NOT gate. Then this is a NOR gate, right? So it is C plus D whole complement, which is nothing but C bar dot D bar. So one thing we can see is that the one expression in the output that is nothing but C bar dot D bar and is getting added with something, right? So G2 should be a OR gate, right? And here what do we want now? We want a AB. So that my final answer would be AB plus C bar D bar. Is it clear to everyone till here? So we have established that G2 should be a OR gate. Now let's say we have the input A bar, we have the input B bar, and we have a box, for example, and we want AB as the output. So what we can have is we can either have a NOR or we can have a NAND to C. So let's say we are having NOR. So NOR, let's say the inputs are A bar and B bar, so it will be A bar plus B bar whole complement. And using the De Morgans, it will be A double bar dot B double bar, which is nothing but AB, right? This is what we want actually. So if G1 will be NOR gate, then this A bar B bar input will give me AB as the output. And this is C bar D bar already here, and the OR gate here will give me Y as AB plus CD. Hence the G1 should be a NOR gate. So option A is the correct answer. Is it clear to everyone? Okay, what part is not clear? Shall I explain later again? Okay, let me explain again. So as I said, maybe I can use a highlighter here. Yeah. So I mean the basic things that we have is A and B are the inputs. So
Our voice is very low, sir.
Is it the case with everyone? My voice is very low.
Yes, sir. Your voice is very low.
Okay. Is it better now? Okay, yeah, fine. So
Okay, sir.
yeah, so what I'm trying to say is, let's say my inputs are A and B, so the NOT output will be A bar and B bar. This is very easy. And if the inputs are C and D, then the NOR gate will give me output of C plus D whole bar. That is basically equivalent to C bar dot D bar, which is I have written here. Now, since the output is having AB plus C bar D bar, so what I said is, to get this plus of the C bar D bar, we should have a OR gate. And the second input of this OR gate should be AB, so that the final answer would be AB plus C bar D bar. Is it clear till here? Whosoever has asked me to explain again. Yeah. So if this output or the input of this G2, if you want AB, and we have input as A bar B bar in this G1, so what I have done is I want the input to be A bar B bar and output to be AB. So if I use a NOR gate, then my output is coming to be AB. So that's why the G1 should be a NOR gate and the G2 should be a OR gate, which is option A. Okay, yeah. So let's move ahead. So the next problem is, what is the primary cause of glitches in digital circuits? So we have already, I mean, gone through the hazard. So what was happening due to the delays in A and A complement, we were getting those different types of hazards and different types of unwanted outputs that we actually don't want. So the variation the most of the glitches that we come is due to the gate delays. So option B is the correct answer. I mean, this is just a theoretical problem. I hope it is clear. Let's move ahead. So now the next problem is the Boolean function AB plus CD is to be realized using two input NAND gates. The minimum number of gates required is what? So I've already got some of the answers as B. Okay, so let me try to explain you in the simpler form. So whenever you see, let's say, the problem here is AB plus CD, which is nothing but a SOP form. Sorry, not R, SOP. So you should always do a AND or implementation. And whenever you see, for example, a POS form, which is something like A plus B, C plus D, you should always do a POS implement. I mean, a POS form, you should always do a or an implementation. I'll try to explain what do I mean by this. So for example, here what do we have? AB plus CD, and what we want is we want NAND gates. So first we should always make this, since this is SOP, I am writing R again. So if this is SOP, it is very easier to realize using NAND gate. So SOP and NAND are complements, always complements each other. So what I was trying to say is your problem is Y is AB plus CD. So you should always do AB is a AND, CD is again a AND. So it is A, B, C, D, and then the sum of these two. So here you can see the output is AB plus CD. So as I said in this slide that you should always do a AND or implementation. By that I mean the first line of the circuit should be having the AND, the second line of the circuit should be having OR. And just now to simplify this using NAND gates, what you do, always bubble out every of the input and output. So this means, so let's say I have a NOT gate and I have a NOT gate again. Let's say I would have an input A here. So what will be the output here? Let's say Y. A, right? Because this is like a buffer only. So I have just added two bubbles on each of the output and input node. That is nothing but the same circuit only. So we have this as a NAND gate, we have this as a NAND gate, and we have this, which is something like this. So we can also see what is this. So let's say this is A, B, for example. So here the output will be A bar plus B bar. And I can also write this as A dot B whole bar, which is nothing but a NAND gate, right? So this is equivalent to actually a NAND gate. Is it clear to everyone? So this is also an AND gate. Sorry, this is also an AND gate. This is also an AND gate. So what do we want? We want three NAND gate to realize AB plus CD. So option B is the correct answer. Similarly, if we would have wanted, let's say, AB plus CD using NOR. Let me ask you this question. So the problem is now we want to realize A plus B times C plus D using NOR gates. How many gates, minimum gates do we require? Please type your answers in the chat box. I'll repeat again. I want to realize A plus B times C plus D using NOR gates. How many gates are required? I got one answer as 4. So let's wait for some more answers and then I'll try to make the circuit out of it. Okay, so mostly answers are 3 now. So as I said, whenever you have been given a POS form, that is very easy to do NOR. So as I was saying, SOP, it is easier to do the NAND formation, and in POS, it is easier to do the NOR formation. So as the problem stated, A plus B, C plus D. Because I already told you should do a OR and implementation. By that, what I mean is the first line of the circuit should be OR gates. So this is A plus B, this is C plus D, and the end of this is A plus B times C plus D. So now this is nothing but a OR and implementation. And now what you can do is you can again bubble this out. So this is also equivalent to a NOR gate. You can try it out. This is a NOR gate, this is a NOR gate. So again, 3 NOR gates are required. Is it clear to everyone? Okay, great. So yeah, the answer would be someone trying to say something. Okay, thought I heard something. Fine. Okay, so the next problem is this: identify the logical operation performed by the given circuits. So again, this is very easy. Please let me know the answers in the chat box. You can take 2 minutes maybe. So I've got a lot of answers is A. So yeah, let's see, because this is very easy problem. So what do we have in the first circuit? We have A and B as an input, and this is a NAND gate. So here the input will be A dot B whole bar. And as we said, this is nothing but equivalent to a NOT gate. If it is shorted, the output will be AB. So this is nothing but, sorry, the output will be AB. So this is nothing but a AND gate. Similarly, we have A complement here, B complement here, and we have A complement dot B complement whole complement, that is nothing but A plus B, which is our OR gate. So A is AND gate, B is OR gate, which is option A. This is easier, I guess. So let's move ahead. Okay, so the next problem says the minimum number of 2-input NAND gates required to implement a 2-input XOR gate is how many? So try to draw different types of circuits in your notebooks or whatever copy and pen you are carrying, and let me know what is the minimum number of NAND gates you think that we require to make a 2-input XOR gate. Okay, some are saying 5, some are saying 4. Okay, let's see then. So what do we want is we want no we do 5. So so it says 2-input NANDs using, sorry, 2-input XOR using 2-input NAND. So what do we want to make? We want to make XOR from NAND. XOR is A B bar plus A bar B. Let me try to make that. So what do we want? We want A B bar and then A bar B, right? So it is somehow equivalent to AB plus CD, where let's say this B is B bar. I mean, not, let's not write like that. So it is, let's say, is something like PQ plus RS, where this Q is B bar, this is A, then this R is, for example, A bar, and this S is B. So we'll do the same and or implementation, but what do we want? We want some of the complement of the circuits in the input. So instead of having B as an input, first of all, let's do that. Whatever we have done before, let's do the and or implementation. So if you remember in the previous question, this was giving me AB plus CD, right? Or I can write here for simplification, I can write PQ plus RS. So now I want the complement of the input here and the complement of one of the input here. So what I can do is I can provide the complement of both the inputs like this. Sorry. So this is A, B, this should be A, this should be B. Yeah. So if you now try to find the output of this thing, it should come out to be A XOR B, or A B bar plus A bar B. So the minimum number of two input NAND gates required are 4. Option A is the correct answer. And yes, as someone suggested, I think if the question would have been NOR, so the answer would have been 4, because we want one more to again. Let me make that also to simplify. So let's say XOR from NOR, it would have been a question. So we would have done the same thing. So let's say this is AB, and then so this is again A, this is again B. This would have been A X NOR B, and then we would have a complemented OR. Okay, I'm not able to draw somehow here. And this would have been given me A XOR B. So 5 NOR gates. And here it's 4 NAND gates. Just to give you a shortcut, I mean, just to, if there is some objective problem and you don't want to do it again and again, let me give you a table. You can learn this table and just write your answers. Not and or NAND nor XOR XNOR. So we know that NOT gate we can use 1 1 to make them. Then AND gate, for NAND gate it's required 2, because 2 times of NAND is AND only, and it's 3 NOR, then 3 2. Then for NAND to NAND it's 1 only, because NAND is NAND already. For NOR to NAND it's 4. Similarly from NAND to NOR, and NOR to NOR is 1. And at last, as we said, NAND to XOR it's 5, but from NOR it's 5, XNOR it's 5, and it's NOR from 4. So you can learn either of the line, and then it's just basically the diagonal elements. Okay, what I'm trying to say is this. So this is diagonally related, this is diagonally related, this is diagonally related. So either line you can learn one of the columns and you will be able to remember all of them. So this is like a shortcut table to remember two input NAND NOR formation. Is it clear, everyone? Okay, great. Let's move ahead. So the next problem is again a simpler problem. It says the logic circuit shown in the figure below can be minimized to what? I'll give you maybe 2-3 minutes and then I'll also solve it. Please try on your own side. Okay, so I'm getting mixed answers. Some are saying B. I can see some are saying, okay, all of them are saying B only. There's one answer which is D. Let's see. So maybe I can try to solve here only. Let me zoom this out. So this is a NOT gate. So here we have X. Here we have X bar. Here we have a dot. I hope you can see this. So the input to this particular thing will be Y bar. So here I'll get the output to be X plus Y whole complement. So it is a NOR gate basically, which is having the input X and Y complement. So the final output here, what I can write is X bar plus X plus Y bar whole bar and then the bar, because this is again a NOR gate. I hope it is clear till now. So it is, I'll write again in bigger font. So now I can use the De Morgan's. So this will be X double bar dot X plus Y bar double bar. So it is nothing but X times X plus Y bar, which is nothing but X plus X Y bar. And I can take X as common, so it will be 1 plus Y bar. And this is X times 1 and nothing but X. Oh, so the input is X and the output is also X. So this is a buffer circuit. So we call this as buffer. So the answer is option D. I am not sure why some of the people are saying X, Y bar as output. Please clarify. Is it clear to everyone? It is half adder of full adder kV number of AND gates. Okay, so for example, half adder, I'll tell you like by speaking only. So half adder has a one XOR gate and one AND gate. So you can add them up. So XOR gate requires 4 NAND gate and one AND gate requires 2 NAND gates. So the total will be 6. So you can do something like that and you'll be able to solve that. So since it has two different output, you can have two different number of expressions that can be solved. Okay, so let's move to the next problem. It says a maximum noise voltage that may appear at the input of the logic gate without changing the logical state of its output is termed as. So again, this is a very theoretical problem. You can see this in your theory lectures also. So the maximum noise voltage that may appear at the input without changing the logical state of input. So this is nothing but noise immunity. So option B is the correct answer. So this is noise immunity. Okay, I think we still have some time. So we can do some of the hazard problems now, and we can relate it using K-map also. So let me write one problem. So which kind of hazard occur in this Boolean expression? So hazard we need to tell. So the option are again three options: static 0, static 1, dynamic, and the fourth option is no hazard. So first, second, third, fourth. So this is the problem, and the expression is given by, I've not given the options. Wait, I've not given the problem. How have you written the answer? A bar C bar D bar plus B C bar D bar plus A bar C D plus B C D. Okay, so let me try to explain this problem by myself because I want to explain you the concept of K-map to check whether there is no hazards or not. So just to verify, I mean, how can we do that is in, so from the expression, the steps to do this is, first step is make the K-map. The second step is ensure all adjacent ones are in same group. So if this happens, then there is no hazard in the expression. And if it does not happen, then you have to ensure that all the adjacent
Sir,
ones, yes,
sir, please tell this one with clarity,
yeah, yeah,
with clearly, sir. With
yeah,
example.
yeah, I'll explain with example, don't worry. So I'll explain what this exact, what this line means exactly. So let's take this example, like for this problem only. Let's make a K-map out of it. So let me do that. So it has four variables. So let's make that. So it's A bar, B bar, A bar, B, A, B, A, B bar, and we have C bar, D bar, C bar, T. Let me write 2, 3, 10, 14, 15. Okay, let me rewrite the expression here. Let I have written all bar, then B, C bar, D bar, A bar, C bar, D bar, B, C bar, D bar, A bar, C, D, B, C, D, plus B, C, D. Okay. So once we have that, we'll fill out the K-map. So the first is A bar, B bar, A bar, B bar, oh sorry, A bar, C bar, D bar. So A bar is these two, C bar, D bar is this. So these two one will come from the first term, which is this. So let me use some other thing. So the second term is B, C bar, D bar. So C bar, D bar is this column and B is here and here. So this one and the additional is already there. So this is from the second term. The third is A bar, CD. So CD is this column and A bar is this and this. And the final one, maybe I can use red only, BCD. So CD is again this and B is here and here. So I filled the K-map now. So what I can do is I can make different, I think I cannot make any quad because there is no four combinations. So I can make this pair and this pair. Similarly, this pair and this pair. I hope the K-map is already clear to everyone. So now once you make the K-map and all the pairs, you need to check, are there any adjacent ones that are not in same group. So if the answer is no, then your expression does not have any hazard. So by this line adjacent one, what do I mean is you need to check everyone. For example, let me use the highlighter. Yeah. So this one is adjacent to this one and they both are in the same group, right? This one is adjacent to this one and they both are in the same group. This one is adjacent to this one and they both are in the same group. This one is adjacent to this one and they both are in the same group. So can we say that are there any adjacent ones that are not in the same group?
No, no,
Yeah.
all are in the same group.
Yeah. So the answer would be there is no hazard in the expression. So here the answer would be no hazard. That is option 4. Is it clear to everyone?
It would be a static one also, na?
No, there is no hazard in the problem since there is no adjacent one that is not there in the K-map.
No, sir. I asked that it would be static one also.
No, there is no hazard in this expression. That is what I'm saying.
Okay.
Yeah. Static one is one of the options if that is what you are referring to. But the answer is no hazard. So let's
Sir,
do,
that means,
yeah.
sir, that means if any adjacent one, that suppose if any adjacent one is not covered by any other group,
Yeah.
then it is there is no hazard.
Yeah, if it is covered, then there is no hazard. If it is not, then yeah, there is some hazard, and we need to figure out what type of hazard is it by solving. But yeah, if it is not, there is no one that is not in the same group, then yeah, there is no hazard. We can make sure.
Okay, sir.
Yeah, so let's do a problem quickly. Maybe one last problem, which is maybe the final problem for today. So now same thing we need to. So the problem is realize the minimized hazard-free implementation. So we need to make an expression now for a function which is, let's say, ABCD, which is hazard free. That means it is not only minimized, but it is also hazard free. So the expression is given by M0 to, sorry, 0 2 5 6 7 8 9 12 13 15. So this is a problem and we need to make a minimize hazard free implementation. That means first of all we'll make a K map that, as I have already told you, then we'll make all the possible coords and pairs, and then whatever the expression comes, even if there is any one which is not covered by the adjacent ones, we need to make those expressions also in that particular expression so that it is also hazard free as well as also minimized. Is it clear to everyone whatever I've just said?
Sir, once repeat, sir.
Okay, so what I'm trying to say is you have given a problem, you will make a K-map, right? And then you will make all the quads and pairs possible, and then you will say that this is the minimized form, something like this, maybe blah blah blah. But we need to make sure that it is also hazard free. So to check that, we need to make sure that there is no one or there is no adjacent ones that are not in the same group. If it is happening, then we have to add those terms also, like make redundant pairs to get the hazard free implementation. So it will be not exactly minimized, but it will be minimized and also hazard free. So we'll have some extra terms if there are no common ones that are not in the same group. Clear enough?
Yes, sir. Yes, sir.
Yeah. You just try to make the K-map and let me know the final expression. And then we can move ahead. Maybe I can give you 2-3 minutes, all of you, to solve. So let me only give you two options because this would be a long answer. So first option is A C bar plus BD plus BD plus A bar C D bar plus A bar B bar D bar plus B bar C bar D bar A B C A bar C D bar plus A bar B bar D plus. Yeah, so these are the two options, either A or B is correct. So let me also try to start to do the problem side by side. So we have 2, 5, blah, blah, blah. Okay, so let me make the K map. Let's write A bar B plus C. For that way, we should make sure that it should be in the same group. Not should not be, but should be. So if there is anyone which is not in the same group, then yeah, you have to make sure that it should come in the same group. Like you have to make redundant group for that. I'll explain that maybe by the example also. But yeah, let's see. So you all should have already got the answer, maybe the minimized form at least. So you can type that in the chat box if possible. So now the options is 0, 2, 5, 6, 7, 8, 9, 0, 2, 5, 6. Okay, let me do one thing. Let me use some different color so that it is visible. 0, 2, 5, 6. Yeah, I'll explain this. Just see this example. 0, 2, 5, 6, 7, 8, 9, 12, 13, 14, 7, 8, 9, 12, 13, 15, 12, 13, 15. Yeah, okay. So let's make the pairs and different things one by one. So one thing that I can clearly see is one quad is this. Is it clear to everyone? I mean, I think you should have also done the same. So this is, let's write with the same pen. So this is B and D. The second quad that I can make is maybe this, which is A C bar. Yes, is there any doubt? Whosoever has raised their hand. Okay, A C bar plus BD. So I've already got one answer, A bar CD and A B bar D bar. Okay, that's great. Now what I can do is I can clearly see I can make this as one, right? And I can make maybe, yeah, just let me just first write this. So this is A bar C D bar, and the last one that I can make is, yeah, I can use red ink only. I can make either like this particular thing with this or this with this. So let me make maybe this only, these two. So both of them can be the answers. But yeah, so now my next term is A bar B bar D bar. Like this is what we do in general using the K map. But now what we need to do is we need to make a hazard free minimization. I hope this is cleared. Yeah. So now for hazard free, we need to check each and every one. So we'll do that. Let's see. So for example, this one, maybe every adjacent one. So this one is adjacent to this and they are in the same group. or group or quad, whatever it is. So these four are in the same group, right? These four are in the same group. This one is adjacent to this one and in the same group. But this one, like the one I'm highlighting, and this one are adjacent, but they are not in the same group, right? Is it clear? These two, the ones that I have circled, these are adjacent, but they are not in the same group, right?
Yes, sir. Yes, sir.
Yeah, so we need to, sorry, we need to explicitly make this pair so that they come in the same group. So there is one more term that we need to add, which is A bar B, and this is C. Are there any one other ones? Okay, yeah, one more I can see. So this one and this one, they are also adjacent but not in the same group, right?
Yes, sir.
Yeah, so we need to make this pair also. So which is something like, maybe I am making this with purple. So this is P bar, sorry, let me not write that. P bar, C bar, D bar. Now is there anyone which is left, which is not in the
Sir,
same group?
5 and 13, sir.
No, 5 and 13 are already in the quad. You see this yellow one, 5 and 13
Okay,
are in
okay,
the
sir.
same quad.
Okay. Yes, sir.
Yeah, so I think we have not left with anyone. So now this is, so let's say these four terms are the minimized form, actually minimized. This is what you have written in your answer if you have not known about the hazard. But these overall system is the minimized plus hazard free implementation. Is it clear to everyone?
Yes, sir. Yes, sir.
Okay, so the answer
Yes, sir.
would be BD plus AC bar. I think the four terms are same. AC bar, BD, A bar, C. I think till here it is same. And then the answer is B bar, C bar, D bar. Okay, this is also same. The final term is A bar, B, C, which is this. So the option B is the correct answer.
Sir, it is for hazard free. If it is for static hazard or dynamic hazard, how we can?
Yeah. Then you need to actually solve the problem out. Like you need to see whether which type of hazard is this. So, for example, you need to check each and every condition. Maybe okay. So maybe I'll do one problem maybe in the next particular week for this whether to check. Maybe I can give you a problem. You can check. Let me give you an example. Let's say the question would have been something simpler, which is A plus C, C bar, for example, B plus C plus CD. Let's say this would have been a question to make it easier. So we would need to check whether it is static 0 or static 1 or no hazard. Oh, sorry, not no, but dynamic. So for static, what do we want? Static 0, we want A bar. I mean, A bar will confuse you. So let's write P bar. For static 1, we want P plus P bar. For dynamic, we want P plus P bar. So how we can find it? We need to like write different values. For example, in this problem, if I write A is equals to B is equals to and D is equals to 0. So what will be the output? So this is
Sir,
0.
sir, once repeat, sir. How
Yeah,
to identify static
yeah.
zero, static one?
Yeah, I'm doing that. So let's say this is the question and you need to identify static 0, 1 or dynamic, right? So static 0, we know that if this terms comes, then it is a static. If this terms comes, then it is static 1. If this terms come, then it is dynamic. Is it clear till here?
Oh, P bar है
Okay, sir.
P plus P bar. Oh,
Yeah. So now to make this P bar, so as you can see, there is A in the expression, but there is no A bar, right? So A bar cannot be the expression. B is there.
Sir, one doubt, sir.
Yes.
That means in the XOR, automatically static zero will be there.
In what?
XOR gate. Why? Because A B bar.
No. You need to have same multiplication. You need to have A bar, not A B bar.
Okay. Okay, sir.
Yeah.
Okay, sir.
So I'm giving you example. So let's say in this example, if you keep A, B, and D both are all of them is equals to 0, so you will be left with C bar times C plus 0, right? If you keep all of them as 0. Is it clear? Sorry. I have kept A0, B0, and D0. So I am left with C bar, right? Is there any
Yes,
doubt
sir.
in
Yes,
that?
sir.
So that means it is having a static 0 hazard. Similarly, for static 1, I want P plus P bar. So what for P plus P bar, I can do A is equals to 0, I can do B is equals to 1, and D is equals to 1. So let's do that. So if A is 0, then the first term will be C bar, the second term will be 1, and the third term will be C. So what is this? This is C plus C bar, right? Is it clear? So this expression also has a static 1 hazard. Similarly, for dynamic, what we want is P bar plus P. So if I do maybe A is equals to 0, P is equals to 0, and D is equals to 1. So when A is 0, it's C bar, when B is 0, it's C, and when D is 1, it's C. So this is dynamic, right? So basically this expression has all hazards. Is it clear to everyone?
Yes,
Yes,
sir.
sir.
Okay, yeah. So if there is no further doubts, I think we can wrap up the class for today. And yeah, we'll meet next week.
ओ
Just
सर, एक्सक्यूज मी सर,
yes.
वो जितनी भी क्लासेस हैं आपकी, इसके वो पीडीएफ मिल जाएंगे विद सॉल्यूशन?
Yes. So I upload it like regularly on that NPTEL Drive portal that they have already given you, or you can join that WhatsApp group. It's already there, I think.
ओके ओके सर, थैंक यू.
Yeah.
Sir, one more, sir. Next class, multiplexes and all those you are going to cover, sir.
Yes. So the next class will cover what was the topic? Let me see. Yeah. So I'll be covering some of the multiplexer is week 6. So I'll be covering some of the arithmetic circuits and code converters. So it's a similar assignment problem that have been given. I'll go through it and cover the same only.
Excuse me, Bhaiya.
Yes.
Yes. So in the previous question, you have said that we are proving that it is a static one and static zero like that, sir, or else that expression is a static one or dynamic like that, sir.
Yes.
Can we get the recorded video of this class?
Yes. So it's regularly uploaded on the YouTube uh, channel. I've already given the link and all of those things.
Are
Okay.
we proving that it is a static one, zero, or dynamic, or else we are identifying?
Yeah. So let's say the question is in a way that what type of hazard is this expression have. So we are trying to see if it has static 0, 1 or dynamic. So we are trying to identify it only, and we have come to a conclusion that this particular expression has all the hazards.
Okay, Bhaiya, thank you.
Yeah, no problem. Let me stop the recording.